All right, hello and welcome to Unit 2, Lesson 6, 2D projectiles. We're now going to be dealing with diagonal components of projectile motion. So essentially we're going to take what we did last lesson, except now we're going to be breaking components up even further. Now, this is the last lesson in the Unit 2 series. So really everything we've done up until now has been building up to being able to solve this style of problem. You can expect in the future we're going to be using these similar properties more, and so gaining some level of mastery over this is going to be fairly important moving forward. So let's see what we have in this problem. It gives us a golf ball, and this golf ball has a speed of 78 meters per second at 23 degrees above the horizontal. All right, I'll sketch that in just 1 second. We'll keep going. We're going to be determining the horizontal distance this ball travels until it lands. Okay, so I'm going to sketch a little schematic here. And what we have is a ball that's just being hit down a driving range or a golf course or something. I'm going to also put on a y axis here just so it's a little bit more clear. And we'll add in the projectile of the ball. So the ball says it's going 23 degrees above the horizontal. So horizontal going above, something like this. Okay, I'm not going to make it quite as long. All right, and that's a little bit more than 23 probably, but it'll give me a little bit of space to draw. Okay, this angle here is known to be 23 degrees. We also know that the magnitude of this line is 78 meters per second. Okay. It's moving ahead like that. So this ball, you can imagine, this is the initial trajectory, but it's going to move along. It's going to increase in height, taper off, and it's eventually going to come back down and hit the ground over here somewhere. And I can extend this ground out a little bit. Okay. Now the question is, how on earth do we go about solving how far this thing goes? All right, this is what our final answer is going to be. Final answer is going to be asking, what is this displacement? Okay, well, there's a lot of information in here that we haven't talked about yet. We know acceleration due to gravity, for example. We in the past have done a little bit of symmetry work, right? So the initial velocity going up is going to be the same as the initial velocity coming down, as long as it's going from or coming from and going to the same relative height. And we have this, which we're going to be able to break up into x and y velocities. So this velocity is actually essentially giving us two velocities once we break it down to our vector. And that's what I want to start with. So this 23 degree 78 meter per second, we should actually split up into both x and y components. So realistically, we have vi in the y direction. Okay, so we'll call this VIY. VIY, and that we don't know yet, but we can solve really quickly. We also have initial velocity in the x direction. So sketch that one under here. We'll call that VIX. We also don't have that, but we'll solve it really soon. Okay, I think I have basically everything sketched out that I want. Now all we have left to do is do a little bit of solving. Figure we might as well just solve these values first. Then we're going to know how fast this is going up. And we're essentially going to split this problem into a ball being tossed straight up with the VIY and then coming back down. And then the ball going up and coming back down, is going to give us the value for our time. Once we have that, we can do the x direction. And the x direction is going to be using this VIX as a constant rate of motion. And we're going to multiply that VI times the time that we get over here. Velocity times time is equal to displacement. Okay, so in order to determine the x, we have to use values in the y, because the y is what's telling us how long this thing is airborne for. And then if we know how long it's airborne, we can multiply the time by the horizontal velocity. Okay, let's go about doing that. Let me clear this off here and start by finding initial velocities. This is a fine color. I have it in green there, I guess. So we'll do VIY. VIY works out to be it's opposite and hypotenuse. So opposite hypotenuse is sine. So sine of 23 degrees is equal to our VIY value over 78 meters per second. So VIY is equal to 78 sine 23, which works out to 30.477. Okay, that's a useful value. Let's save that to x in magenta. So VIX is equal to the cos of 23 It's equal to VIX over 78. And so we have VIX equal to 78 cos 23 works out to 71.8 meters per second. Okay, which makes sense because this thing is traveling more horizontal to the x-axis than it is closer to the y-axis, right? So we'd imagine more speed to be along this horizontal long side. Okay. Awesome. Now we already determined that we're going to be using the y components to solve for time, and then taking that time and mixing it in with the x components to solve the x displacement. Okay, keeping your x's and y's separate is a skill in itself, so it's going to take some practice. Let's do the vertical y-axis here. So y components, I haven't used blue yet. Y component. Okay, what do we have in the y? We've got initial velocity in the y, which we just solved here. So VIY is equal to 30.477 meters per second. VF. Okay, so now we're dealing with that symmetry issue, right? So if we kick something up in the air, toss something up in the air at 10 meters per second, and the place, if we catch it from the same height, coming back down, when it hits our hand, it should be going the same 10 meters per second. Same thing here, we're whacking this golf ball up into the sky, It's going to peak, and it's going to be 0 meters per second right at the peak in the y direction, and then it's going to start to fall again. So what we end up getting is final velocity in the y direction is also going to be equal to 30.477 meters per second, except this final velocity is going to be in the downward direction, so we're going to call it negative 30.477 meters per second. All right, since this is on Earth, I guess it doesn't specify, but I'll let you know it's on Earth. Our acceleration is going to be negative 9.81 meters per second squared. And it's negative again because up is our upward direction. Gravity is working downwards. Okay, we discussed we want time because we're going to use it in part 2. So time is unknown and we want it, which means our last component, displacement, don't know, don't care. Nice. Okay, well, we've got our things. We need to find a formula that excludes displacement. And the formula that worked for me was, what color is going to be decent that we haven't really used? Orange. Okay. Color that seemed to work well for me was acceleration in the y, which I don't know if we really have to specify that it's in the y, but whatever, is equal to VF y minus VI y all over time. Do a little swaparoo on this A and T to give us the formula T is equal to, I'm going to drop the Y subnotes, but you can keep them if you like them. It's equal to VF minus VI over A. So T is equal to, VF was negative, so negative 30.477 minusing a positive value, so minus 30.477 all over negative 9.81. So our time works out to 6.21 seconds. I almost boxed that, but that's only a useful value. Okay, we know how long it takes for this thing to get punted up, come back down, 6.21 seconds, which means that the halfway point, if we're interested in that, which we're not, would be 3.105 seconds, but not the most important value for us. Okay, let's wrap this up. Let's do back in red. Solve the x component. So divider wall here, x component, and make that look a little bit more like an x. We're going to say, well, our formula is going to be distance is equal to velocity times time, because this is a constant velocity flying for some period of time, 6.21 seconds. So our known values, we have Vx is equal to 71.8 meters per second. And that's what we solve for up here. Okay. We also have time, which we solve for down here, 6.21 seconds. And we can just solve for displacement then. So displacement is equal to 71.8 meters per second times 6.21 seconds. Displacement works out here to, I didn't actually work that one out myself, so let me punch it in. 71.8 times 6.21 comes out to 445. I'll write it out. 445.878 meters. And this question, if I wrote this out correctly believe had 3 sigdigs. So we're going to round this thing off to 446 meters. And that is the final answer.